Okay, today is operation with algebraic vectors in R2, and we're going to find out that many of the algebraic operations on vectors, once we have them as Cartesian vectors, are very straightforward. So by applying the methods that we developed for addition, subtraction, and scalar multiplication of geometric vectors, you could prove the following. These are very easy to prove using geometric vectors, that if you got two vectors, u equals x1 comma y1, and v equals x2 comma y2, and k is a scalar. If you want to add two vectors, you just add their x components and add their y components. You want to subtract two vectors, you just subtract their x components and subtract their y components. And if you want to multiply the vector by a scalar, why, you just multiply the k in. You just take that thing and distribute it across the vector, just as you would expect they would. And some of this seems like overkill, like, of course you would, maybe, is what you're thinking. But there is some stuff coming in next chapter that isn't obvious. And so we have to lay the foundation here of making what is obvious, go through it and very clearly state what is obvious, and then the stuff that maybe doesn't come quite as easily will make a lot more sense once we've laid that foundation. So if you find this easy and straightforward, great. What a nice treat that we've come all this way in math and we got some nice easy stuff today. So for instance, evaluate the following vector operations. If we want to add a vector 3, 4 with a vector 2, negative 5, we literally just add the x's, 3 plus 2, and add the y's, 4 plus negative 5. Certainly don't need to show that step, but I do here just so you get the idea. And subtracting vectors, the x component, we go 7 minus the 4. The y component, we go negative 1 minus the negative 2. Watch out for subtracting a negative there. 3 minus 1, or sorry, 3 comma 1 there, because negative 1 subtract negative 2 is positive 1. And then if you want to multiply things by 3, you just multiply both things by 3. So nice. Vector operations, very, very nice. Vector algebraic operations. Now, the distributive property was proven in a video earlier, and it was very, I won't say it was complicated, but there's a lot to it to try and prove the distributive property. But using the vector properties that I've done here, the operations on algebraic vectors, it's actually a very straightforward proof algebraically. So let me go through proving that the distributive property works for two vectors a and b. So what I'm going to say is I'm going to let the a vector here be what I did above, which is that'll be x1 comma y1. And then I'm going to let the b vector be equal to x2 comma y2. Pretty standard setup. And what we're saying there is this a and b vector can be anything. These whatever those numbers are, and by the end we'll see what do we do with those numbers in this situation. So I'm going to start with this line here and hopefully end with that line there. Okay, I'm going to start with m times a vector plus b vector. And the a vector here, I need a big set of brackets here. The a vector here is x1 comma y1. And the b vector here is x2 comma y2. I like using different sizes of brackets. It allows me to see what the heck I'm doing there. And then my new algebraic property tells me that to add two vectors, I just add the x's and add the y's. And my new distributive property tells me if I've got a number out front, this m out here, that I just multiply it by the x components and multiply it by the y components. So what I get is a vector that's called m x1 plus x2, m y1 plus y2. And then these are just numbers in here. This is not vectors we're talking about. There's just numbers. And so I can distribute those like I always have. mx1 plus mx2, my1 plus my2. That 2's a little too big there. There you go. And then I'm just going to do the reverse of what I did before, which is to separate this back into two vectors, now with the distributed m in them. So now my first vector is mx1 comma my1. And the second vector is mx2 comma my2. I've just done the reverse of my algebraic properties there. Instead of adding them together, I've broke them apart into two vectors. And then I'm going to do the reverse of distributive, which is multiplying that k in there. I'm going to bring the m out front. And so I'm all done. There's m times the a vector plus m times the b vector. So nice that we can use distributive property on vectors, and so easy to prove here now. And so this simplifies the proof. Well, I don't know if it's simpler. Maybe more straightforward is the right word, because the other proof was long, but not too bad to follow. Now, if you want to determine the magnitude of a vector, if this one has its tail at 1, 2, so there's the tail, and the tip is out at 7, 6, so that's out here. So there's the vector there. And if I want to find its magnitude, well, I can just use the Pythagorean theorem, or length of a line segment, same thing we've always done in this situation. And so I'll formally write here is what you would do is you'd go square root, the length, I'll call this vector u, and so the length of u will be the square root of the delta x squared plus the delta y squared. That is just the straight up Pythagorean theorem. So the delta x here is 7 minus 1, and the delta y here is 6 minus 2. And so I get square root of 6 squared plus 4 squared, 36 plus 16, root 52. 6 and 4 is 36, 16. Yeah, that's right, root 52. And now, a little bit of practice on your simplifying radicals here. This can be broke into root 4, root 13, which is 2 root 13. I'm not saying there's a lot of that coming, but geez, when we get the chance to mention it, we sure want to here. So that's how we go about finding the magnitude of a vector, how long a vector is. And there it is formally there. We've got a vector x1, y1, another point, both points, x1, y1, and x2, y2. There are 2 points there. If we want to find the magnitude of the vector, we just do that. And so with a vector like this one, 9, negative 4, which is, you don't have to do the delta x and the delta y. It's already done for you. So I'm going to call this vector u. And so the magnitude of u will just be the square root of 9 squared plus negative 4 squared, 81 plus 16, root 97 here. I don't have to do any simplifying there because there's no nice perfect square that divides into 97. That's done. Okay, something that will seem easy, and it really is easy, and it's just so powerful that you've got to see it. We're going to introduce 2 vectors called I and j here, and I is the vector 1, 0, and j is the vector 0, 1, and they're in the picture there so you can see what they look like. Both I and j have magnitude 1, and this came up with the homework. So if you had trouble with the homework question that talked about unit vectors, this is what a unit vector is. It's a vector that has exactly length 1, and I and j are perfect like that. They both have length 1. And the formal definition of I and j are right there. Now, the power of I and j might not be clear yet. It's going to take a little bit of time, so you just have to trust that this is a really cool way to write vectors and a really powerful way. So any algebraic vector can be written as a linear combination of I and j. And what I mean by that is any vector you come up with, and this vector they said was 4, 2. There's 4, 2. Well, that can be made up of 4 i's. There's the I vector. And then 2 j's. And hopefully this picture is enough to convince you that any vector you go to draw, you can make up as any number of I, not any number, you can make up as some number of i's and j's. For instance, 4, 2 is equal to 4 I vectors plus 2 j vectors. And if you think, okay, so that's the i's is just the x component and the j's is just the y component, yeah, just that easy. And they want the magnitude of the vector here. So the magnitude, and again, I'm going to give this vector a name, u. And so the magnitude of u is equal to the square root of 4 squared plus 2 squared, just the Pythagorean theorem there. I get root 16 plus 4, root 20. A little practice on my simplifying radicals here. I see this breaks into root 4, root 5. And so I get 2 root 5. Not a ton of that coming up, but just a mention on that so when it comes up. This is all that stuff in one box here. Any algebraic vector with components a and b can be written as ai plus bj, and its magnitude is square root of a squared plus b squared. So not too bad here, all setting up to do this stuff in 3D tomorrow. So check out that homework, zip your way through it. If there's any questions, follow up, and have a great day.